In this video, I'm going to go ahead and walk you through how we can graph by hand our equation y equals x cubed minus 6x squared plus 9x plus 1. So we really have two questions that we want to know, which is what does the first derivative tell us about this graph, and what does the second derivative tell us about this graph? Because where the first derivative has a sign change, positive negative or negative positive, that's going to tell us information about the function, whether it's increasing to decreasing, which would be a maximum, or decreasing to increasing, which would be a minimum. The second derivative, if the second derivative is positive or negative, that's going to tell us a change in concavity and our inflection point. So let's go ahead and start by looking at the first derivative and getting any information that we can about this graph. So the derivative of y is going to be 3x squared minus 12x plus 9. And I'm going to go ahead and set my derivative equal to 0 because I'm trying to find that critical number where my derivative changes from positive to negative or vice versa. So to solve this problem, this is going to use factoring. So I'm going to go ahead and start by factoring out of 3. 3x squared minus 4x plus 3, which means my two factors are going to be x minus 3, x minus 1. So where this is equal to 0 is going to be where x is equal to 3 and where x is equal to 1. These are my critical numbers. This is where I'm going to go ahead and check to see whether or not I have a sign change. So I set up some test intervals, so from negative infinity to 1, from 1 to 3, and from 3 to infinity. These are going to be my test intervals. And I'm going to go ahead and find some test numbers within those intervals. Choose easy ones. So I'm going to choose things like 0, 2, and 4. They don't have to be 0, 2, and 4. They just have to be a number within each of these stated intervals. And now I can take each of those test numbers, and I'm looking for the sign of my first derivative. So if I take 0 and I plug it into my first derivative, I can choose to plug it in to the derivative that looks like this, 3x squared minus 12x plus 9. But it's actually going to be some easier math if I actually just look at the factored form of the derivative, which is 3 times x minus 3 times x minus 1. So if I go ahead and I plug in 0, I get 3 times 0 minus 3, which is just going to be a negative number, and 0 minus 1, which is going to also be a negative number, which means that the derivative is actually positive on that interval from negative infinity to 1. So f of x, or the way that my function is behaving y, is going to be increasing because my first derivative is positive. I'm going to do this again with my other two numbers, 2 and 4. So I take 2, and again, I'm using this factored form up here, and I'm plugging that in. So 2 minus 3 is negative 1. And I don't care by putting negative 1, and if I plug in 2 and I get positive 1, I don't care about the actual value. I just care whether or not that is a positive number or a negative number, because that tells me, for example, in this case, that my function is decreasing since my first derivative is negative. I now go ahead and take 4. I plug that in. 4 minus 3 is 1. 4 minus 1 is also positive. It's positive 3. So that's going to be positive, which means I'm increasing. So my function is going to be increasing to decreasing. So increasing to decreasing, something like that, means that I'm going to have a max here. And then from decreasing to increasing means that I'm going to have a minimum here. So I've identified that we have a max at x equals 1 and a minimum at x equals 3. I don't know those y values. To find those y values, I would have to go back and plug those in to my original function. So let's go ahead and do that. If I have y equals x cubed minus 6x squared plus 9x plus 1, if I plug in 3, if I plug in 1, I'm going to start with 1. If I plug in 1, I get 1 cubed minus 6, 1 squared plus 9 times 1 plus 1, which is going to be 1 minus 6 plus 9 plus 1, which is going to give me negative 4 plus 9 is 5. So I know I have a maximum at 1 and 5. And I can go ahead and plug that 3 in to figure out what my minimum value is going to be. So x cubed minus, nope, not x cubed, we want 3 cubed. 3 cubed minus 6 times 3 squared plus 9 times 3 plus 1. So that's 27 minus 54 plus 18, nope, plus 27 plus 1. So negative 54 plus 27 is going to be a negative 27 plus this 27 plus 1 is just going to be 1. So I have a minimum at 3 and 1. So I have my maximums and my minimums, but the second derivative can also tell us the change in concavity, which if I go from a maximum to a minimum, I'm likely to change concave down to concave up, but I can find that inflection point where that exactly happens. So my second derivative, I need to find my first one again, so my first derivative is 3x squared minus 12x plus 9. So to take the second derivative is going to be 6x minus 12. If I take that second derivative and I set it equal to 0, I'm finding that critical number where I'm going to change sign. That's going to give me my information about my inflection point. So if I move 12 over, I get x is equal to 2. Now, an inflection point only occurs when there is a sign change in that second derivative, which there is going to be. We'll see here in a second, but it's always good to just go ahead and check. I sound so confident because of what was happening here with my maximums and minimums. And parabolas are fairly predictable. So I still have my intervals here. You can see my critical number changed to 2. So I'm going to go ahead and choose test numbers within my new intervals. So again, choose easy ones like 0. I'm choosing 3 here. It doesn't have to be these exact ones. It just has to be something that fits in either one of those intervals. So now I'm looking for the sign of the second derivative. So I'm taking 0 and I'm plugging it into my second derivative. So 6 times 0 minus 12 is just going to be a negative 12, which means I'm concave down. That makes sense because right before 2, I have a maximum at 1, and a maximum is going to give me a graph that's slightly concave down. I guess not slightly, it's exactly concave down. Now I'm going to go ahead and take 3 and plug that in. So again, I'm plugging it in here. 6 times 3 is going to be 18 minus 12, which is going to give me a positive number, and I'm concave up. So that means that there is an inflection point because there's a change in concavity at x equals 2. To figure out that the y value, I'm going to have to plug 2 back into my function. So if my function is x cubed minus 6x squared, copying that down. Let's go ahead and plug that in. So 2 cubed minus 6 times 2 squared plus 9 times 2 plus 1 is going to be 8 minus 24 plus 18 plus 1, which gives me 2 plus 1, which is 3. So we know that my inflection point is going to occur at 2 and 3. So I have my minimum point, my maximum point, and my inflection point. So now I get to go ahead and graph what I think this sort of looks like. It's by hand. So at 1, I have a maximum here. At 3, I've got a minimum. And at 2, I have my inflection point. So my graph's going to look something like this. Oop, let me go through those points. I did a decent job going through those points. There we go. So my max, my min, and my inflection point. And that's how you graph it by hand.